Hello students, welcome in the series of lectures in the subject VLSI technology. Today we will discuss the topic physical vapor deposition. So what is that physical vapor deposition that we will discuss? Students, as you know, we are studying metallization and we want to deposit metal. We want to make gate contacts, we want to make contact metallization, we want to do interconnection metallization. So how metal is deposited, okay, onto the semiconductor to make these contacts, okay. So the process through which this is done, okay, is called physical vapor deposition. So metals, specifically metals, are deposited using physical vapor deposition. Okay, so there are two processes, two methods by which physical vapor deposition, the metal can be deposited over to the semiconductor, okay, to make contacts, are vacuum evaporation and sputtering. Okay, so these are the two processes that are pretty much common and they are used in both of these techniques, both of these processes, vacuum evaporation process or sputtering process. Remember, these two processes are used to deposit materials, metals onto the semiconductors. Okay, not onto the only to the semiconductor, but also they can be used to deposit it onto the silicon dioxide also in order to make gate contacts. Okay, so there are basically common steps in both these processes. What are those steps? So the first step in both these processes is to convert solid into gaseous or vapor phase. First of all, we have a solid, means whatever metal you want to deposit that is in the solid form, it is first converted into gaseous or vapor phase. So how you will convert solid into gaseous or vapor? So here you want heating, okay? So some mean of heating is required in both the cases, both the process. Now once that metal is converted into gaseous or vapor phase, then it is transported from the source, where source means where the metal is present, to the substrate where you want to deposit it. Once the metal has been transported in the gaseous phase onto the substrate, okay, then it is condensed onto the substrate. Okay, why? How it is condensed? Because the substrate is kept at a lower temperature. Okay, and the metals are vaporized at their melting points. Okay, if the material is sublime, then the sublimation temperature. Okay, so substrate is kept at a temperature lower than that, pretty much lower than that, so that condensation will take place, and the gas or vapor in which the metal is present, it will condensed onto the substrate. Okay, it is followed by nucleation. After that, this is followed by nucleation and growth of the film. So these are the three steps that are common in vacuum evaporation and sputtering processes. So what is done in vacuum evaporation process? So in vacuum evaporation process, a film is deposited by condensation of vapor onto the substrate, which is made and maintained at lower temperature than vapor. Okay. So remember the first step. What was the first step in these processes? The metal in solid form is converted into gaseous phase or vapor phase. How it is done? It can be done using resistive heating, RF heating, electron gun, or laser heating. These all approaches can be used, okay, to convert metal into gaseous phase or vapor. Okay. Uh, Once this has been converted, then it is transported from the source to the substrate, and then condensation takes place. This is very simple vacuum evaporation. Okay. So how it is done, in which apparatus it is done, we will discuss later. By this method, by this evaporation method, we can also deposit alloy or mixture of two or more materials by using two or more independently controlled evaporation sources. Okay. Next is the sputtering process. So what is done in the sputtering process? So in the sputtering process, we have a target material. This is basically metal, which is to be deposited onto the substrate. This is substrate. So this target material is bombarded by energetic ions first. So first this is bombarded by energetic ions. So energetic ions bombard this metal. Due to this, sputtering process takes place, and metal atoms of this metal goes out. Okay, sputtered. These goes out due to the bombardment. Okay, some atoms are released in the metal side. When these atoms have been released, they are condensed onto the substrate to form the film. This is simple sputtering deposition process. Okay. There is some problem with this sputtering mechanism. That is, when you are bombarding with energetic ions, okay, so defects may be produced in the metals. Okay, so sputtering mechanism can also be used to deposit alloys onto the substrate as well. Okay, uh, sputtering is carried out at relatively high pressure, then the very low pressure compared with the vacuum evaporation process. In vacuum evaporation deposition process, pressure is very much less in the chamber. Okay, in comparison with if we use sputtering process, the relative pressure comparison to the vacuum evaporation process is pretty much high. Okay, so what is the apparatus? So this is vacuum evaporation deposition. So this chamber can be used for vacuum evaporation deposition. So here in this chamber, uh, we uh, we have a process chamber, okay, in which a circular stand like thing is there on which substrate are placed fixed. This is the source material for metal, okay, and from here gases are passed on to the source. Okay, so first of all, by using this roughing pump, the pressure inside the chamber is reduced. Okay, so roughing pump reduces the pressure from 1 atmospheric to zero point 0.1 Pascal. Okay, uh, in addition to the roughing pump, we can also add oil diffusion pump, which can bring pressure down to 10 raised to the power minus 5 Pascal. And with the help of liquid nitrogen trap, the pressure can further reduce to 10 raised to the power minus 7 Pascal. Okay, so in case of vacuum evaporation deposition, the pressure is from 10 raised to the power minus 5 to 10 raised to the power minus 7 Pascal. Okay, so chamber shown here is a bell jar, a stainless steel cylindrical vessel, okay, which is closed as top and sealed at the base. So we start with 1 atmospheric pressure, and we use this roughing pump. Okay, so roughing pump, and this by using roughing pump, chamber is evacuated by using roughing pump. Okay, now After this roughing pump, this high vacuum pump are used. Okay, so with the help of this high vacuum pump, the pressure inside the chamber is reduced to a great extent, up to the limit 10 raised to the minus 5 to 10 raised to the minus 7. As the appropriate pressure in the chamber is reached, okay, uh, substrate is heated slightly. This substrate, which you can see, it can be heated slightly, okay, and as the pressure is has been reduced here, okay, so uh, the material is deposited onto the substrate. So this is the process that is done here. Now there are some physical phenomena that is happening. So there is one law that is called cosine law of deposition. So in cosine law of deposition, what is seen here is that let's say you have a source here. This is the source, and onto this source, this is a very small negligible area, that is dAe. Here, this is the substrate that is placed here. Okay, so if you make this geometry like this, so from this source, the metal will deposit it onto the substrate. Okay, so there are two angles, one is phi and one is theta. So phi is the angle between the normal and the uh, deposition angle. Okay, deposition direction, in this direction metal is depositing. At the distance r, substrate is placed from the source. Okay, okay, so by the sine cosine law of deposition says that the mass deposited per unit area is given by me upon pi r square cos phi into cos theta, where me is the total mass of evaporated material. Whatever material that has been evaporated from there, the mass of that is me. Okay, r is the distance from source to the substrate. Okay, now if both the source and the substrate are mounted on a spherical surface of radius r naught, okay, so in that case, suppose we have a spherical surface r naught, and here onto that surface, let's say this is substrate, and let's say this is your source. So these are mounted on the same spherical surface. So let's say this is the center. So the radius of that spherical surface is, let's say, r naught. This is r naught. This is the center. This will be also r naught. Okay, so it is seen that the distance between the source and the substrate is r. So it is seen that cos theta will be equal to cos phi, and it will be equal to r upon 2 r naught. So if you put these values here, then what you find the value of rd equals to me upon 4 pi r naught square. That is mass deposited per unit area is like this. Okay.